All right, let's pick up where we left off last time. Remember, last time we introduced quantization. Quantization is a mean of discretizing the signal in an amplitude domain, making it discrete in the amplitude domain. It's kind of dual of sampling. Sampling is doing the same thing in the time domain, but the quantization does make the signal discrete in an amplitude domain. There are two kinds of quantization, scalar and vector. We're going to limit ourselves in this course to a scalar quantization. Now, what I'm going to draw here, it will take me a little bit of time, is what is called transfer function of the quantized. And the reason I'm drawing is twofold. First one is I'm going to be referencing it through several things that I show up today. And the second reason is the way how it's drawn in your book is incorrect. Right? So it's flipped by I think, mistake. So that's why I want to actually have it drawn on the board. It will take me some time, so it's just I suggest you follow along, but you also have it in notes. Now, what is the transfer function of the quantizer? It actually shows you the input-output relationship in a quantizer. You would have here input signal, x, and that signal would occupy certain range of values between minus u max and u max, right? I'm going to assume that the signal is symmetric about the origin. That doesn't have to be the case, but for most signals, it is the case. Let me just bring a little bit inside. So, what happens here? Let's say this is, let me just make sure. Okay, so this is, I'm going to have an 8-level quantizer because I'm going to put 8 distinct intervals here. This is an interval 0, 1, let me just actually do it this way, 0, 1, 2, 3, 4, 5, 6, 7. So I have 8 intervals. And then here's how it works. Anything that is in the interval 4 will get this value. And then everything that's with interval 5 will get this value. And then everything that's in interval 6 will get this value. Interval 6 this value, and interval 7 and above we get this value. On the other hand, this is what happened here. Another delta here, and then 0 and below. Okay. So that's my input-output characteristic of the quantizer. How do you interpret this? Well, as I said, everything that if the input falls within this interval here, it will have this value. And I'm going to call this value as x4 quantized, right? If this value here is going to be x5 quantized, this value here x6 quantized, this value here x7 quantized, then this value is x3, then this value is x2, this value x1, and then this one, the last one, or let's say maybe the first one, is x0 quantized. So there is infinitely many possibilities for input, right? Because input can be any continuous value, right? Between or even outside minus u max to u max. But as the output of this, I'm going to always get just 8 different values, right? It's going to be either x0 x1 all the way to x7. So there's just 8 outputs to this quantizer here. So this is an output signal, and obviously the point of greatest interest to us is this. When we perform quantization, obviously we're representing the signal value with something that is not exact signal value. We're making some error. The point of greatest interest to us is how large is this error and how do we control this error? Is this something that is within our control? To illustrate what is happening here, let me draw this error here as a function of the input signal. So this is your quantization error. And let's see here. If the signal is at this middle of this interval here, then it will be, the output value will be the same as the signal itself. Is this inside our or it's outside? No. We can tilt it this way. So there is only one point in the particular quantization interval where the output value exactly matches the input value, right? Even though you're doing quantization, the value is exact, right? This is the middle of this interval. Everywhere else in this interval, you're making an error. How does this error look like? Well, this is a quantization error. Let me look the value of that error for this interval. It will look like this, right? It is going to be the largest at the ends of the interval and the smallest in the middle, right? And then for the next interval, the error would repeat. It would look like this. For the next interval, the same behavior. But then for the last interval, this grows unbounded, right? Because for all the points that are to the right of this U max, you're going to always put out x7 quantization. So the error is going to grow unbounded in this direction. And hopefully this would happen very seldom, right? Because you hope that your signal is going to be limited, you know, within a certain range before you do the quantization. And then the same thing, but the opposite happens on this side. So this is behavior of your quantization error as a function of the input, right? So this is your input signal value x, and this is how large the quantization error is going to be. Once again, there will be these points where it crosses 0. These are the points where the input signal is right in the middle of the quantization interval. And for all the other points, there will be some error. The error is largest at the edges of the interval, and then it kind of alternates between within a certain range. Now, there are some deltas here. This is what we call delta, the input, and delta, I guess, U. And this is the quantization step in the output, delta Y. Right? Those two, you know, for quantization. And then, if you look at or let's make it so that it is delta in both ends, because it's a uniform quantizer. So, and we can see that the delta is largest here, 1/2 delta, and then -1/2 delta. So at the end of the interval, the error is the half of this interval between the quantization lengths. So the error is between -1/2 delta here to 1/2 delta on the other side. Right? And delta is the size of the quantization interval. Okay, so that's the transfer characteristic. Again, how do you navigate through this? If I supply a certain value, at the input, that value will fall somewhere on this axis here, and as a result, at the output of the quantizer, one of these 8 values will show up. So what quantizer does, it transfers the continuous range of values from the input into a discrete set of values that we can obtain in the output. And in this case, the number of output values is 8. So we call this 8-level quantizer, or as you will see a little bit later, 3-bit quantizer, because you can represent 8 values with 3 bits. All right. So what is of great importance to us is something called signal to quantization noise ratio. Signal to quantization noise ratio, or SQNR. That's the principal metric of how much of an error is introduced by your quantizer. So here's how we start. We say X, that's your input, and it's a random variable. And since we are now concerned only about magnitude, I guess it's also a random process, right? But since we are only concerned about quantization in the magnitude domain, I can treat this as a random variable, because all I care is the PDF, the distribution in the amplitude domain. So X, since it's a random variable, we're going to assume that we know the PDF X of X, or just PDF of X. So that's known to us. XQ is going to be your quantization level. That's what comes up as an output of this quantizer here. And NQ is going to be difference between XQ and X. This is what we're going to refer to as quantization error. Okay. What causes quantization error? We do, right? Through the process of quantization, we're actually taking the sample, which in theory is sampled to the infinite precision, and replacing that with a level that is one of these discrete values, replacing it with the closest one, right? So there is some difference between what was actually sampled and what was actually passed to the processing. This error is irreversible. Once you do that, you don't know what the original sample was, right? So it has all the characteristics of the noise. And in practice, we call that quantization noise. But it's the noise that is introduced by the process itself. And as such, we have a pretty much good control of what is the magnitude of that noise and what are its statistical properties. To determine what is the quantization, signal to noise quantization ratios, SQNR is power of the signal of X divided by power of this NQ. And that's the quantity that we need to calculate. It depends on properties of signal itself. So it will depend on the PDF of X, and it will depend on a number of quantization levels that we have in our quantizer. Power of the signal is, we know how to do that. Power of signal is essentially expected value of X squared, which we know to calculate. This is X goes from minus infinity to plus infinity, X squared PDF of X dx. So that's the power of signal. Now, the power of the quantization noise let's call that, so this one I'm going to call PS, power of the signal. P and Q is going to be expected value of NQ squared.
What is that
which is expected value of x minus x cubed squared, right? Where this is the input and this is the appropriate quantization level. And we know how this is just another function again of a random variable here. So this becomes integral when x goes from minus infinity to plus infinity, x minus x cubed of x squared times pdf of x dx. Okay, let's understand this. I'm looking at the power of the quantization noise. It's going to be x minus the appropriate quantization level. But the quantization level, as x goes from minus infinity to plus infinity, the quantization level changes as a function of x, depending in which interval x falls into, right? So this is what we need to evaluate to determine the power of the quantization noise. So how do we do that? Well, how this changes is based on these intervals. So there are, in this case, 8 different intervals that we need to consider. So let me call this point here the middle point, x0. The middle point here, x n minus 1, right? The middle point of these two intervals, this is x1, x2, and so on, right? This is x n minus 2, where n in this case is equal to 8, right? In general case, it's going to be 8. So I'm associating the middle value with each one of these intervals. And then I'm going to split this integral here into essentially n distinct intervals where I'm going to integrate by individual intervals of your quantizer there. So, to make a long story short, here's how this can be rewritten. Power of the quantization noise becomes an integral when x goes from minus infinity to x0 minus delta over 2. So that's the beginning. So that's that unbounded curve to the very left of the entire range over there. And over there, the error is going to be x minus x0 squared times pdf of x dx. And then I have sum when I goes from 0 to n minus 1, x minus xi quantized squared times pdf of x dx. And then for the last one on the very right hand side, the last interval over there, I'm going to have integral when x goes from x n minus 1 plus delta over 2 plus infinity x minus x n minus 1 at squared times pdf of x dx. Right. So this is these are all components of the quantization error. There is an error before you enter the quantizer. Hopefully this one is small by the virtue that the pdf of x is essentially equals 0. The signal does not take the values outside of the range that you present to the quantizer. The same thing here. So hopefully this is the most important part of the quantization error. So we're going to introduce some simplifying assumptions.
Do those add?
Say again?
It's a summation of all those? It's addition?
Yeah, so there's an integral here sorry, xi minus delta over 2 to xi plus delta over 2.
Xi.
Right? So these are all of these intervals that are
X1, X1, X2.
yeah. So these are these guys from here to here, from here to this error that the first term covers from minus infinity up to this point. So that's the first term. Then this is, these are all of these summation terms. And then the last term goes from here. This is the last term, right? And then you essentially have n middle terms, one term before, and one term after. Right? So there's total of n plus 2 terms. So here are the simplifying assumptions that I'm going to introduce. The first one is saying that PDF of x is identically equal to 0 when x is smaller than x0 minus delta over 2 and x is greater than xn minus 1 plus delta over 2. What does this mean? This means that the input really stays within a range of your quantizer, right? And that's not unrealistic. Here's an example. You all program some microcontrollers, right? And we say, okay, this is a standard analog input. What does that mean? For 0 to 5 volts, right? So if this is coming as an output of some sensor, the sensor will always give you the value between 0 to 5 volts. Right? So that means that the probability of you getting outside of the range of the quantizer that is attached to that particular pin is going to be 0. Right? So that's the assumption that I'm introducing here. The second assumption that I'm going to introduce is quantization step is small. Small, right? So this delta is such that PDF of x is approximately the same as PDF at this one value xi for x between xi minus delta over 2 to xi plus delta over 2. So if I have a large number of quantization levels, then across this one small interval associated with the single quantization level, PDF approximately stays the same. In other words, I can assume that its value in every point of the interval is approximately the same as the value in the middle of the interval. Now, for this, I don't have any physical justification as of yet, but when we start doing some formulas, you will see where this will become very handy. For our particular example here, this may not be the case because I have only 3-bit quantizer, right? So I have only 8 distinct values. But if you have, let's say, 8-bit quantizer, you're already talking 256 different levels. So these levels are very close together, and the PDF changes very by a small amount across this entire interval. So the second assumption is also a reasonable one. So now that I use these two assumptions, I can take this signal to quantization noise ratio calculations further, just so that we don't lose sight. This is the end of the first part. This is how I calculate the power of the signal. The reason why we're doing all of this is to estimate what the power of the quantization noise is, so that we can estimate SQ out. So this one I'm putting aside, and then I'm working on the second part step by step. So we're still working on noise. So let's go.
Excuse me, Professor.
Uh-huh.
I think I remember something about quantization step is small. In fading, actually, you have the example same like PDF of x almost equal like PDF of x, but I forgot which fading.
Fading, everything is analog there. We haven't talked about quantization whatsoever.
I mean, like when you have a calculate signal to noise ratio and fading, you use this.
We always use PDFs and stuff like that. So
right.
that is all over the place. But over there, we didn't deal with quantization effects at all. But we did use PDF, so that might remind you of that. So let me actually leave this on. I'm gonna need that, and then let me just continue with calculating quantization noise for it. So the power of the quantization noise, now approximately sum when I goes from 0 to n minus 1, integral when x goes from xi minus delta over 2 to xi plus delta over 2. And then I have x minus xi squared times PDF of x dx in that particular interval. But since this interval is relatively small, then this PDF of x does not change much. And then I can take this PDF of x outside of the integral, treat it as a constant. So this is approximately sum when I goes from 0 to n minus 1, PDF of xi, and then integral when x goes from xi minus delta over 2 to xi plus delta over 2, x minus xi squared dx. Now this second integral is now very easy to solve. It's one of the simplest integrals, so let me just solve it. So this is equal, I goes from 0 to n minus 1, PDF of xi, now as a constant, and this is x minus xi, 3 over 3, xi minus delta over 2 to xi plus delta over 2. Now let's substitute the boundaries. So this becomes sum when I goes from 0 to n minus 1, PDF of xi. When you substitute the top boundary, you see xi and xi will cancel, and you have delta over 2 cubed. So this becomes delta cubed over 8 minus. When you substitute the second boundary, xi will cancel again, and you have delta over 2 cubed, but because it's minus, it becomes plus. So it's delta cubed over 8 divided by 3.
So this PDF up here, is this PDF of xi inside the
No,
integral?
xi's are constants. Xi's are these guys. The sentence, right? It's PDF, this PDF is associated with the input, probability
So
density
it's the
function.
same. It's the same probability density function of x.
Yeah.
But then when it comes out, it becomes a probability density function of xi.
Why? No, this is PDF of x. I cannot draw this. Evaluated at the
At xi.
point xi.
Okay.
Here's what is happening, right? Let's say these are all of your xi, right? And you have quite a few of them in any realistic scenario. So now let's say this is how PDF looks like. I'm looking at interval around this xi. Let's say this is your interval xi minus delta over 2 to xi plus delta over 2, right? That's the interval surrounding particular quantization point. If I now look at what is happening to the function here, if this interval is small, in other words, if delta is small, then the changes of this guy are so small that I can assume that this is a constant, across this entire interval. And once I assume that it is constant, what is the best value to say? Well, I'm going to assume that everywhere in this interval, this is approximately PDF of evaluated at the middle, right? That's the value, right? So this is your actual PDF. So I'm substituting this PDF with a whole bunch of, how should I say, staircase, with a staircase approximation. And then the smaller the delta is, these two become smaller to one another, right?
So the quantization, we don't have a PDF of the quantization noise, per se.
No, we don't. But we have PDF of
The input.
we have the PDF of input, and then we have that quantization noise is a difference between input and constant for that given interval. So you kind of already have it, right? That's what we're actually doing, right? Because remember, what we are here. What we're trying to do is this: power of the quantization noise is going to be integral when x goes from minus infinity to plus infinity, quantization noise as a function of x times PDF of x dx. This is n cubed, quantization noise is a function of the input, and this is expected value of, actually we need to do this. So it's the expected value of the function of the input, and the quantization noise is obviously, size of the noise is a function of the input. Give me input value, I can tell you how large the quantization noise is. And this goes back to our review, how do you actually determine expected value of the function. You put the function in here, attach the PDF, and then you crunch the integral. The random variable here is x.
But the PDF is still of x, not of the noise.
Correct, but we can, do, if you want to determine the quantization, the PDF of the quantization noise as well.
Mhm.
Now, I'm going to talk about it a little bit later, because even if we don't go explicitly derive it, what we're going to end up concluding is that quantization noise has a uniform PDF, as long as these quantization intervals are small. And I'll come back to that, right? Come back to that. So it's an interesting follow-up of this second assumption. But so far, this is what we're trying to evaluate. And remember, the way how we evaluated this, we actually explicitly stated what this is. This is x minus xi. And then because xi changes in each individual interval, we split this into n plus 2 intervals, and then we kind of neglected 2 of them because we're saying, well, theoretically, you're allowed this, but practically you're never going to be outside of the range of the quantizer. And then for these middle intervals, we say they're so small that I can neglect the variations of the PDF, take that out, and then we end up with something that is trivial to evaluate, right? So let's take this one step further. This delta cubed and delta cubed over 8 gives me delta cubed over 4, and then this gives me delta cubed over 12. But I'm going to write this in a particular way. I'm going to say this is sum when I goes from 0 to n minus 1, PDF of xi times delta, and I'm going to put this in a bracket and put this to be delta squared over 12. Now, let me ask you this. What's the value of this integral? 1. Why is it 1?
The entire.
Yeah. Here's what I'm doing. I'm taking the PDF of xi, which is the value here,
The
and
area under the
multiplying
curve.
that by delta.
Area.
So I'm
Area.
taking this area,
Right.
and I'm doing that for every interval. So if I add all of these areas, what do I get? I get something that is approximately 1. And the smaller the delta is, closer to 1 this is, right? So this is approximately 1. And you end up with a famous relationship that everybody knows. Power of the quantization error is delta squared over 12. Right? Delta squared over 12. And even people who don't know this derivation, remember this. Because that's
Like EMC square.
yeah, one of those things. So now that we have the power of the noise, let's illustrate this using 2 different examples with this whole, or maybe let me just finish this by saying, now that we have a signal and then we have a noise, we have that SQ and R. SQ and R is going to be 12 over delta squared integral x goes from minus infinity to plus infinity x squared times PDF of x dx. That's a signal to quantization noise ratio. And just like you expect, right, it is inversely proportional to delta. The smaller the delta, the larger signal, the smaller the noise. So the signal to quantization noise ratio grows up as the delta becomes small. Right? the smaller the steps, the better you are in quantizing, therefore your signal to noise ratio goes up. You're introducing less of a noise through your quantization process. Now, to illustrate, I want to point out a significant thing here. And to do that, I'm going to look into two examples. What I would like to highlight here is the importance of this PDF, right? How does the PDF of the input change your signal to quantization noise ratio? The reason why I'm doing that is to justify non-uniform quantization. Because right now, all of our steps are the same size, right? And this will give me a certain performance that I was able to calculate here. But I want to test this on two different examples, and you will see that depending on the statistics of your input signal, your signal to quantization noise ratio will change. It will change as a function of the PDF of the input signal. We want to understand why that's the case, and then see how we correct for that. Okay? So let me test this whole all of these formulas using two simple cases. One is going to be the case where your input is distributed uniform. So test case 1. We're testing, right? So it's not, there are only two cases. There are infinitely many cases, but we're testing the case 1. Here, I'm going to say that my x follows the PDF of x, which is equal to 1 over 2 u max, right? U max. Or let me just do this, u0. And see, I already made it u0 here. Let's make this u min. Because in theory, they don't have to be the same, but they're always the same. Where here, u max is equal to u min is equal to u0. And this is true for x smaller than u0 and 0 otherwise. What is it that I'm saying here? I'm saying that the value of the input is uniformly distributed between these two extreme values, right? So it takes the value across the entire range of possible values with the same probability. Okay. So if we assume that. So let's calculate now what is the signal to quantization noise ratio here. First, the power of the signal is going to be equal E actually x squared, or I'll comment on that in just a second. So this becomes an integral from, let's say, x goes from minus infinity to plus infinity in general, x squared times PDF of x dx. But in our case, this becomes 2 times integral from 0 to u0, x squared times 1 over 2 u0 dx. Right, because our x is now uniformly distributed. The distribution is symmetric between minus u0 and plus u0. So the PDF is just 1 over u to 0. I'm integrating from 0 to u0 and then putting 2 here, right, to get the power of the signal. This integral is very easy to evaluate. So expected value of x squared, which is the power of your signal, is going to be 2 and 2 cancels, 1 over u0 comes outside, and this is x cubed over 3 between 0 and u0. So this gives you value u0 squared over 3, right? Because 1 u0 is going to cancel with this u0 here. So that's the power of your signal. I don't know if you have noticed, but I'm making a slight error here. Where is it that I'm kind of cutting the cord? We're having two signals. One is the input signal, which is your X, and the other one is output signal X quantized. When we talk about signal to quantization ratio, proper way to define is the power of the output quantized signal defined by the power of the noise. So, but if your quantization steps are small, then the power of the output signal and power of the input signal are essentially the same. All right, so that's the power of the signal. Power of the noise, from graph here, from, I guess that chart or graph over there, we have that 2 times U0 is going to be equal Q minus 1 times delta, where Q is the number of quantization levels. Okay, so that's how many quantization levels you have, and then Q minus 1 times delta gives you this full range here. So therefore, if I now from here I can express U0 as Q minus 1 times delta over 2. And then the power of the signal here in terms of number of quantization levels and delta as U0 squared, so this becomes Q minus 1 squared times delta squared divided by 12. Right, so that's the power of the signal now expressed in the number of quantization levels and quantization step. And now if I substitute the final result in here, you get that your SQ and R, in this case, is what power of the signal divided by the power of the quantization noise. Power of the signal is Q minus 1 squared delta squared over 12. And power of the quantization noise is what? Delta squared over 12. So look at how beautiful the result is. Q minus 1 squared. If I express my signal to quantization noise in dB, then SQ and R expressed in dB is going to be 10 log of Q minus 1 quantity squared, which is 20 log of Q minus 1, which usually Q is much larger than 1. So this is practically 20 log of Q. Right? That's how we estimate signal to quantization noise ratio for relatively large Q. Now let's look at an example here. Example to an example. So let us assume that Q is equal to 256, very common number. This is 8-bit quantizer. You have 256 different levels. So what is the signal to quantization noise ratio? It's going to be 20 log of essentially 255, which gives you 48 dB. So for a uniform signal, 8-bit or 256 level quantizer gives you a signal to quantization noise ratio of 48 dB, which is quite large, right? The quantization noise ratio. So let's take a look at the next example here. I'm going to assume, so case 2. I'm going to now look at the difference. I'm going to say that PDF of X is equal to 1 over square root of 2 pi sigma e to the minus x squared over 2 sigma squared for x smaller than u0, 0 otherwise. And then for this to work, I'm going to say u0 is much greater than, let's say, 3 times sigma. So your signal is now not uniformly distributed, right? It does not take the values within this range with equal probability. It is mostly focused around 0. And the smaller the sigma is, more focused around 0 the signal is going to be, right? I'm setting this sigma quite small so that the signal is never really outside of this range again. Right? So now, let's calculate the signal to quantization noise ratio in this particular case. Power of the signal is expected value of x squared. What is this in this case? If I have a normal distribution, and the mean is equal to 0, what is the variance? Sigma squared, right? So power of the signal is sigma squared, and I guess your signal to quantization noise ratio is going to be sigma squared divided by delta squared over 12, which is 12 sigma squared over delta. Let's assume some relationship between sigma and u0. Let's say since your u0 has to be greater, I should say much greater, just greater than 3 sigma. Let's assume that u0 is equal to 4 sigma, or in other words, that sigma is equal to u0 over 4. Go ahead.
It's should be delta square or just delta?
Delta square. Delta square. So assume, for example, that your sigma is u0 over 4, right? So now if you do that, then since 2u0 is equal q minus 1 times delta, then from here, okay, so I can say power of the signal, which is equal to sigma squared, which is equal to u0 squared over 16, is equal to 1 over 16. And instead of u0, I can put q minus 1 times delta over 2, and then I have to have quantity squared, right? So that's the power of my signal now expressed in terms of delta and the number of quantization levels in this particular case. Now, when you unwrap this, this becomes q minus 1 squared times delta squared, and then you have here 16 times 4 divided by 64. So your signal to quantization noise ratio in this case is 10 log of power of the signal, which is q minus 1 quantity squared times delta squared over 64, divided by the power of the quantization noise, which is delta squared over 12. And when appropriate things cancel, you end up with 20 log of q minus 1 plus, I guess, 10 log of 3 over 16. Where is 3 over 16 coming from? Well, this 12 climbs upstairs, and then 64 goes downstairs, and you divide both of them by 4. So you get 3 upstairs and 16 downstairs. So this gives you 20 log of q minus 1, and then minus 7.25 dB. Okay? Now, so that's what the math says. But here's where we need to stop, and or let me actually carry this all the way through. Let's assume that the number of quantization levels is 256, just to have an apple-to-apple comparison. So,
So,
For-
excuse me, Professor.
uh-huh.
So in the end, you should submit that 48 dB minus that 2.25 dB. Is that correct?
Where is 725?
Yeah, I'm sorry, 7. So for
Let
48
me finish and then we'll come and discuss this whole thing. So for Q equal 256, in this case, signal to quantization noise ratio is going to be 48 minus 7, so it's going to be 48 dB minus 725 dB. So this is 40. I don't know how did I end up with 4087,
47?
but it should be 4075, right? Okay. So now, so that's math, and I kind of hope that I didn't bore you through all of this. But we have now two examples, and let's kind of look at what those examples are telling us, and then draw some general conclusions here. This is first example. This is the range of my quantizer. The distribution of your input is like this. So it's exercising this entire range. And we ended up with a signal to quantization noise ratio of 48 dB. Now, in second example, this is my quantizer. Again, I have signal, this is my range, but now the signal does not occupy entire range. Mostly it is centered around the origin. So this is PDF of X, and this is X, and this is now PDF of X. Now here, I end up with signal to quantization noise ratio, which is equal to 41 or 40.75 dB. Why is this the case? What is happening here? In the first case, the signal goes through the entire range. So there are places where, if you compare now, where the error and the signal, there are places where signal to quantization noise ratio is relatively small. Like if your value of your signal is relatively small, then the quantization error is significant, right? If you, let's say, if your signal is delta and you're making an error of delta over 2, your error is significant, right? So at the small levels of the signal, your quantization error is large when you compare it to your signal level, right? And this signal here has some of these, but then it has also these values here, where the value of the signal is relatively large, and then the quantization step is so small. So in this part of the input signal range, the signal to quantization noise ratio is relatively large. So on average, you get this 48 dB of the signal to quantization noise ratio. This signal here spends most of its life around 0, right? Why? Because you have this peak of the PDF that says most of the time this signal is focused around 0. Around 0 is where your error is the largest. Quantization error is the largest because the value of the signal is close to 0, and yet error can be as large as delta over 2. So your signal to noise quantization error, if you look at sample by sample, for this signal is relatively large. Therefore, when this signal is quantized with a uniform quantizer, you end up reducing your SQNR. And the smaller the sigma is, right? The smaller the sigma is relative to the range, worse off you are, right? Because that means the signal is closer and closer to the 0, where the errors due to your quantization are going to be large. So here's the important point here. The important point here, first, several that we can derive. First one is SQNR depends on the PDF of your signal. And then the more focus, the more the signal is about the origin, the worse SQNR, because that's saying the more signal is taking small values, that it is going to be impacted by quantization more and more. Why? Because that's where the errors due to the quantization are the largest, and the small values of the input signal. How do we fight against this? Any ideas?
Filters.
Non-uniform.
Go ahead.
But don't we want a large SQNR?
Yeah, the larger the better.
So the one on the right is worse.
Yes.
Worse, yeah. This quantizer, uniform quantizer for this signal is very bad, right? Because it does not take into consideration the fact that the signal is mostly around zero. It ignores that.
Mm.
And then quantizers assume that the signal is occupying the entire range. And it's not. It's very rarely here. So why am I having small quantization steps here, right? So what is the proper way to handle this? Well, you look at the signal and you say, okay, my signal is mostly around zero. So why don't I make delta small around zero? And then because my delta controls the quantization error. And then as I go more towards the outside, where the signal spends less of the time, I can make delta larger there. In other words, live with a larger error, absolute error, towards the edges of this band allowed by signal, and have smaller absolute errors closer to the zero. Relatively, I can keep the errors the same. So as my signal grows in the magnitude, my signal amplitude grows, but my quantization error grows. But the ratio of the two stays the same. And when you start thinking that way, what is it that you're building the case for? You're building the case for non-uniform quantization, right? Why am I keeping this delta constant across the board? It seems that I have benefits that I can derive from keeping delta non-uniform. But what is the fundamental problem with it?
You gotta know your input signal distribution.
Yeah, you gotta actually make quantizer for every type of the signal. You're gonna say, okay, oh, this is voice, so let me pick this quantizer, and it's not gonna work for any other signal, right? So now your quantizer becomes tuned to a particular properties of your input signal. That's not the way how we like things to build in IC circuit design. We want to build one circuit and hit as large of a market that we can possibly hit. So we'll have to look at an alternative approach to how we do that. Before we go there, let me summarize some of the important formulas that we actually put another formula that is widely known, and this is because a lot of times when we speak about quantizers, we don't talk in terms of the number of levels, we talk in terms of the number of bits that are placed at the output for each individual sample. Let me explain what. So if you look at, there are all of these quantization levels, and we can number them, 0, 1, 2, all the way here to n. So this one we're going to represent with a certain number of bits. In this case, since I have a total of 8 levels, I'm going to place 3 bits here. And then, 0, 0, 1, 0, 0, 0, 1, 0, all the way to 1, 1, 1, right? So these are my outputs. So if Q is the number of levels, Q is usually given as 2 to the n, where n is number of bits. Used per sample. And we're talking about, 6-bit, 7-bit, 10-bit quantizer, and so on. So now, we derived that for uniform signal, for uniform input signal, we had that our signal to quantization noise ratio was approximately 20 log of Q. Right, we neglect that Q minus 1 because usually Q is much greater than 1. And then when you substitute this 2 to the n here, you end up that signal to quantization noise ratio is 20 log of 2 to the n, which is n that goes downstairs times 20 log of 2. What is the 20 log of 2? What's 10 log of 2? Yeah, 6. Right, 6. So this is 6n. And that's the formula that everybody knows. When you talk about signal to quantization noise ratio, you say it's 6n, right, in dB. Okay? So if I have a 5-bit quantizer, what is the expected signal to quantization noise ratio, the output? 30 dB, right? Now, when you say 30 dB, and let's say you put your signal and it's not 30 dB, what's the reason?
It's a different PDF.
Different PDF. This is strictly true. Correct, I would say. When PDF of X is uniform. In other words, the quantizer is made to exercise the entire range, or the signal is exercising the entire input range of the quantizer. In other words, it goes from minus U0 to plus U0 with equal probability across the board. Okay? For non-uniform signals, for signals for which this is not true, there would be a penalty. And the penalty is going to be larger for the signals that are focused around 0, and it's going to be, smaller for the signals that are occupying, depending how the signals are distributed. Okay, so let me highlight another trade-off that you should be aware of, and this is SQNR versus data rate. Here's our, when you see this, then you can say, okay, I can make my SQNR as large as I want by selecting n to be relatively large. And the payoff is quite nice. Every time you add a bit, you gain 6 dB, right? So pretty soon you get up with a very good signal to quantization noise ratio. But what is the penalty here? So let's go back and look at what this means practically from our sampling and quantization. Now going back to both domains, looking both time and amplitude. Let's say our signal is band limited. So Fs is equal to W, right? Where W the bandwidth of the signal. Of the signal. Then your bit rate is going to be whatever you're sampling times n. So this is bit rate used to represent the signal. And it's simple. You're sampling Fs at a frequency Fs. Every time you sample, you are giving n bits to each individual sample. So this is your net bit rate that you need to represent the signal. In the case of voice, we had 8 kilohertz times 8 bits per second, or 8 bit per sample. So this gave us 64 kilobits for a voice signal. Now, I know that n can be written as SQNR in dB divided by 6. So your RD is going to be Fs times SQNR in dB divided by 6. So this is where it tells you the price you pay. If you want high SQNR, you pay that in a bit rate, and the relationship is 1-to-1. A lot of times, you actually start from here, right?
Start from the
Start from RB, say how large is my channel, what kind of data rate I can get on the channel. And once you get that, then this is also given based on the bandwidth of your signal. So you end up with how much of a SQNR can I afford, right? And so, for example, you say, okay, my channel supports 40 kilobits per second. I have to sample at 20 kilobits per second, kilohertz, because my bandwidth is 10 kilohertz. So 40 divided by 20 gives you SQNR over 6 to be equal to 2. So SQNR is 2 times 6, 12 dB, and that kind of gives you how many quantization levels you can have for a given signal to meet your bandwidth requirement, your throughput requirements, right? So what I want you to be aware here is how closely are all of these quantities timed, right? Your bit rate, your quantization, number of quantization levels, sampling frequency. There's one more variable that we're going to add, which is a symbol rate. And then a lot of times when you design the system, you're going to actually juggle all of these to pick the right combination, right? And then your symbol rate ultimately related to power, right? So you're going to say, okay, what is the bandwidth of my signal? Well, the RB that I can afford, so that gives you the symbol rate. Then you go work backwards and determine what the transmit power needs to be and do your whole link budget design. Okay, any questions here?
Yes.
Finally.
All
right.
So how many quantizations that we have actually in the real world? Because
Two.
Dynamic and static.
No, two. One is in time and the other one is the magnitude, right? You quantize in time by sampling. You quantize in magnitude by doing quantization.
Yeah, because whenever you have the analog design of circuit, usually we have quantization in ADC. Am I right? Analog to digital.
What we usually do is, most of the time, our electronics, it usually comes with some signal processing boards. On a board, we usually have a DSP of some sort, or in a simple board, it's a microcontroller. And microcontrollers have something what is called I/O ports. And these I/O ports are usually followed by the quantizer, right? Because the arithmetical logical units and everything that calculates in here does not know how to handle analog signals. Simply doesn't, right? Because it's doing multiplication of bits and complementing and all that stuff. So there is an analog to digital conversion that happens at these ports. And what comes with the data sheet associated with a particular microcontroller DSP is how many bits is your quantizer here, right?
Also not the particular, like the data rate, something like that, so it just...
No, it says in the data sheet, this one comes with I/O port that has 10-bit quantizer, right? And the range of levels 0 to 5 volts.
Uniform distribution.
But you cannot manipulate that.
No, uniform distribution is not problem of the quantizer.
But they won't say if it's like a non-uniform quantizer?
It's okay, we haven't got to this point.
Oh.
When we design quantizers, we always design them as uniform. And the way how we deal with the fact that the signal has non-uniform PDF, we pre-process the signal itself. That way you can focus, because remember, A to D converter is the process as a whole. And one of the things that you want in A to D conversion, you want it to be really fast. So you cannot be really messing with signals and different. You have to make it, it's usually some sort of, it can be, for example, a resistor ladder or something really simple so that it can spit out these levels relatively fast. So the way how it is customary to deal with the fact that the signal has a non-uniform distribution is to pre-distort the signal, to change its PDF. And that means let's say your signal looks like this. It has a PDF that is like this, so it's focused around 0. So then you run it through an amplifier that has a characteristic that looks like this. What does this amplifier do? It takes the values that are around 0 and gives them a larger gain, and takes the values that are towards the edge and amplifies them less. So what this will do to this PDF, it will transform the PDF into something that looks like this. Make your signal look uniform. And this is called compression, right?
Right.
And we have these compressions for different signals. And this is what I'm going to talk about next time, how you actually design this and what is the optimum compression, and how you know, if you know PDF, how do you determine the transfer function of this amplifier.
So we don't build non-uniform quantizers?
No, we don't. We build uniform quantizers, and then we have various compression techniques, which we pre-process the signals before we feed them to the uniform quantizer. And maybe you've heard, I'm going to go a little bit ahead, you've heard about mu compression, A compression. These are the compressions that are used, for example, in voice processing. If you feed the voice to the mu compression, then you actually end up making it more uniformly distributed in the amplitude domain, and then we feed it to the uniform quantizer. And you can see that there's, next time we'll see that there's significant benefit that you can get from it.
Last question. Actually, in a theoretical way, what is the purpose of the compression? It makes your signal like something like
Transforms the PDF of your signal from non-uniform to uniform, or close to uniform. So therefore, it's more suitable for uniform quantization.
So make your in particular way, it makes your signal become tight, something like become really
Flatter.
tight or something like that in the behavior of signal.
You're now using musician's terms.
Yeah.
Compression makes your signal tight, right? That's
tight.
how a guitar player would say.
Right.
No, in our terms here, it takes the PDF of the signal, where most of our signals are dwelling quite a bit of time around 0. You all have capabilities of that. Say something, record your voice,
Right.
and then display it in MATLAB, and you will see that the signal is, a lot of times around 0. It is kind of doing this, and then there are your vowels, and then
but
spends
it
a lot of
depends on
time.
your model.
Plot your histogram, and you will see that it has a really peak
Spectrum.
at 0, right?
Right.
So that means it has the highest probability being in a range of the quantizer where the SQNR is the lowest. So that's not good. So what we do is we say, okay, before I quantize the signal, I'm going to amplify it with something that's nonlinear, and take these small values and make them large, and take these large values and pretty much leave them on their own. And what that does, it restores the signal. If you play that back to your ears, it's going to sound really funny, right?
Right.
But it's good for a quantizer.
Like low pass oscillation, something.
And
yeah,
then
like
quantizer would introduce less of an error there, and then you would send that to your system. But before you play it to the user, you have to do the inverse operation. You have to decompress, right? And then overall net effect of that is that you improve the SQNR for the whole system. And what that does is, if you have a system that required, let's say, 12-bit quantizer to operate properly, but now through this amplification and with these nonlinear amplifiers, the compression and decompression, you end up getting the same SQNR, but now with 8 bits, which gives you a much lower throughput requirement on your communication system. And remember, in our world, bandwidth is everything. Right? You would trade pretty much all the processing on 2 ends just to save the bandwidth, because bandwidth translates in money. If you always go through a shared channel, and the smaller the bandwidth you give to one user, more users you can put on that, and then you can get more paid for the same resource. So that's the idea here. We discovered that the SQNR depends on the PDF. We discovered that PDF may actually adversely affect your SQNR, and what we need to do next time is devise an engineering solution for that, and that would be non-uniform compression. Right? Homework problem, assignment 652. probably noticed we left chapter 2 and we're now in chapter 6.
You seem like jump
Chapter
around.
4, yeah. We left chapter 4, now we're in chapter 6.